Hello and welcome to tutorial 4 of this NPTEL course in Reinforcement Learning. I'm Abhivkar. I'm a PhD student at Indian Institute of Science. So today we'll discuss Markov decision process, which we already discussed, but we'll discuss in greater detail. And in last week, infinite horizon Markov decision process and Feldman equation, value iteration, these things are covered, I think, right? So is value iteration covered? Anyone? Am I audible?
Yeah, Vicky, you are pretty good.
Yeah, so I was asking, is value iteration covered in last week?
I skipped the last week's class,
No.
so
No, I don't think value iteration is covered. I think we have reached until the Banach process. So the
Okay, so
proof,
fixed point theorem, right?
yeah, fixed point theorem and the linear. I think the linear process or the linear process converges, yeah, to the optimal solution. That's where we are at.
Okay, so basically finite horizon value iteration is like, it's not value iteration, so finite horizon between finite horizon MDP and infinite horizon discounted. Rewarding.
Actually, there was a mention in one of the classes, one of the videos, that finite horizon MDP makes it a non-stationary process. Is that right?
Yes, so last week tutorial, I think. So, yeah, last week, not last week, I think last week. Yeah. So the last week tutorial. So here I have mentioned this. If you see this reward function. Is that wait. Yeah, here. So this mean reward function and the transition kernel, these all depend on the time, right? So that makes it non-stationary. I mean, uh, the reason is basically, even if it is stationary, that is pH equals to some P for all, and mu h is also equals to mu for all h. Then also the policy will be non-stationary. We can show that. And I mean, the policy could be non-stationary. So, and if you change it to non-stationary transition kernels and non-stationary reward function, then also the analysis does not change. And then also it will be non-stationary problem. The policies will be non-stationary. So in general, we analyze it assuming the process, everything is non-stationary. But for infinite horizon, we do not generally assume that. And yeah, that's one of the main difference.
Thank you.
Okay, so for finite horizon MDPs, um, we have seen the dynamic programming algorithm, and which is basically called value iteration also. So we'll put that algorithm today. So finite horizon MDP is consisting of this state space, shell space, uh, transition kernels, such that the sum of this makes it probability. Is and this is for all SA. This is for all SA. This time. And this is the transition pattern, and then there is the new, which is mean reward function. Sorry, I have made a mistake. But this is from state action and next state. But mu h, which we have assumed that this is a function of state and action. And you can, most of the analysis is done for bounded reward function. So you can simply assume that mu h belongs to the domain of the function. Sorry, range of the function is 0 to 1. And this is for h from 1 to h minus 1 or sorry, 0 to h minus 1 or 1 to h. Which one I used, I forgot anyway. So let's write 0 to h minus 1. Oh, sorry, actually it will be, yeah, it will be 0 to h minus 1. And here also same, h is to 0 to h minus 1. And then the horizon length or episode duration, capital H. So this was this finite horizon NDP. And then we derived the algorithm. Let me write the pseudocode of the algorithm and then we'll code it. If all of you think that coding is not required, then you can tell and I'll skip that part. So you need to input. Input is basically your MDP because this is planning algorithm. To plan the algorithm, you need to know the MDP, right? Input is MDP. And MDP is that tuple, right? Which is, it is denoted by M and specifically that they say, in short, I'm writing P, mu, H. And you need to initialize the value function. If you remember correctly, then what you did is you initialized value function at the last stage, VH. So what we did there, VHS was RHS. That means at HH step, capital HH step, if you are at state S, your value at that step is basically what is the reward you are getting. So using mu, right? Okay. So I missed something in reward. So reward is a function of state and action till till the time capital H minus 1, and at capital H, mu capital H is basically a function of state, because there we are not taking any action. That is called terminal loop. Okay. And yeah, so we'll initialize in the algorithm for uh, value function like that. VHS equals to mu h s for all s in state space. Here our assumption is the state space is finite. So otherwise there is no hope in this algorithm. I mean, at least you cannot compute it. Then what we did is we came from step h to h-1, then h-2 and up to 0. And at 0, we had the value function at start. And if you remember correctly, then uh, I mean, what we did is in every step, whatever was the maximizer action at some state, uh, basically the policy we are getting at that state at that time itself. So I guess it's not clear if you don't remember now, but I think if I write it. So for step H, which is now starting from H, capital H-1 and running to 0, we'll do update this value function. Will not actually update because this is basically value function of step H. So we are not updating the same variable. PHS is max over action mu H is K plus T. So what does that mean? This means you are at state S and what action will take so that you will maximize this sum. What is this sum? This is the current reward. But you are not only worried about the current reward, you are also worried about where you want. In the next step, you will by taking some action, you will get a current reward, and you will land up some next state. If that state is bad, then you are not doing good, right? So I think Professor Ravindran has given an example that
It should
Yeah.
be H-1, right? From the previous state.
H+1, right? We are going backward. So we have started at capital H. And then we are in the first step, we are basically finding the value of step H-1, capital H-1. So you will look at current reward, what you can take, what your, current action, and which will maximize your current reward plus the value going forward. So,
Okay.
okay, is the confusion clear?
Yeah, thanks.
So this is basically expected. Expected while we are taking expectation on next state. Right? Expected next state value. Okay, so these words are not part of the algorithm, but I'm not erasing that. So then you're okay. So I made a mistake. So this process you have to do for all states, right? So there is another for loop involved for state S, for S in state space. For S in capital S, do this. And then we end this for loop. For, and then we have a value function for every state, and we have also seen that which action is maximizing that value, right? So we can here itself we can update the uh, okay. So again, so here itself we can update the policy, which is the best policy for so P star H, because at each step the policy we are finding it may not be same for all the stages. So P star H is equals to arg max. And the same thing, let me just copy and paste. Right. So that way we can get the policy itself. And then we end the for loop. And then what is remaining? What we have to basically do in each step, we are getting a policy. So we have to append the policy to. I think we have not initialized the policy, right? So we have to initialize this pi star as empty set. And each stage we are basically pushing a policy in that set. So P star is updated as PH star union P star itself. So you have a set of policies and you know which policy is corresponding to which step, and you have basically the optimal policies. So not that here we are calling the set of policy as policy, also individual map, that is P star H. This also we are calling policy, right? This is policy. But the point to be noted that is P star H in is equals to 0 to H minus 1. This is also your calling policy. But note that these are very different objects. One is a function, another is a set of functions. Okay, so here we have to end for. And then your algorithm just have to return this return v0, which is the value function at state 0 and I step the optimal policy. Yeah, so that's the thing. And now we'll see a code of this value iteration algorithm or dynamic programming algorithm. Is my screen unshared? No. I hope you can see the code, right?
Yeah, we can see the code.
Okay. Yeah, so this I'll go through very quickly, and I'll not discuss this coding of this MDP that I'll request you to see. And basically the reason I coded this MDP few years, 1 year back, maybe a few years, and I couldn't find any reason for doing this complicated stuff. Maybe there was some reason, that's why I did it. Probably the MDP just doing something trivial. So this MDP were generating randomly, and maybe some trivial generation procedure was giving something. The policy was maybe very bad, like constant policy, something like that. So I did something complicated here, and yeah, please go through the code. If you are like habituated with coding and stuff, you'll understand everything. Okay, so I'll discuss the variables. Just this is number of actions. This is number of states. Here we are saving the transition probability. So here, uh, transition probabilities, since this is finite state action, these are just not metrics. I've written transition probability metrics, so these are like multi-dimensional, three-dimensional things. And this is basically a tensor. And then there is the reward function, which is also we can, okay, reward distribution. The reward distribution is also, I think, returning a matrix. Yeah, that's it. So NP random uniform or mean. So yeah, and state space is basically 0 to ns minus 1, and action space is 0 to ni minus 1. So we are initially using the state. So this is not exactly the initialization. This is just assigning, creating a variable and assigning non-value to it. So this function is what you have to go through yourself and requesting. And yeah. So at the beginning, you have to initialize or the function I am calling it. Yeah.
The reward distribution here is you're saying the size is S versus A. So basically, it means what is the expected reward when you take action A in state S, is it?
No, I think here I have done with deterministic reward. Uh,
Okay, there is no,
okay,
there is no
so
stochastic.
there is no stochastic. You can incorporate that.
So basically, it is just when you are in state S and you take action A, you get this reward.
Yes, the only stochasticity will be coming from the transitions.
Okay.
Yeah, so
So that itself is reward distribution itself is not related to which state you end up in.
no, it will. So this will this reward distribution is basically determining the. I should not call it reward distribution. I should call it something else.
No, that's
Maybe
fine. That's fine. But
no,
whenever
no,
we
no. There
saw
is
the
no
equation,
distribution.
it said expected value of R given S, A, and S prime in the equation. So here it seems like the reward itself has nothing to do with the S prime. Can you?
Okay. Yeah. So yeah, that is also good point. So Professor Ravindran, I think he has kept reward as a function of S A and A prime, S prime. And here just before I mean in the pad I was what I was writing, I was writing mu of S A. So that way it was just function of S and A, not S prime. Okay. Now the thing is, here I have simplified it more actually. I have just kept it function of S. If you see here, this time I'm jumping a bit. So self dot reward is self dot R S. R is a deterministic like a matrix, and I'm just choosing the S component of it. So this, but it was not necessary, right? Because here
What is R there? Self dot R.
okay, R is this matrix. Okay, just a second. Yeah, R is calling this function self dot reward distribution 0 to 1. 0 to 1 is basically the minimum value of rewards, and 1 is maximum value. And this reward distribution, let me actually change the name. It's reward matrix or reward function also find it. Okay, so this is returning S cross A matrix at state S and A. So those are numbers, like say state 2 and action 5. So it will pick the 2, 5 element, that corresponding coordinate element, and that will be the reward basically.
Right. So that self dot reward then is an entire row, is it? R S.
Yes, yes. So I think there is some mistake. Yeah. So it should be, I think, S comma A. Am I calling this A? Okay, action. It's action. Self dot state. Yeah. So I think so for up to reward matrix, we have understood. And at the beginning of starting everything, you need to initialize state, right? Your is 0. So this is basically initializing your uh, process. And then if you take us call this function state and pass the action, then it will update the state. It will basically save this variable s in, sorry, save this variable self dot state in s and then update this state. Okay, now I have understood. This should be s. Okay, so s is replaced. Sorry, state is replaced by next state in this step. Okay, and then we are getting a scalar reward, which is according to the reward matrix R. And then we are returning self dot state and self dot reward to the agent. That's what the agency. And yes, so this is the function to just sample action uniformly. Okay, so just scale it. Run this MDP. Then we are calling an MDP of state 10 states and 6 actions. Let me make it 8. So age is 20. You can increase it to 40. And so here note that we have kept the reward and transition stationary. That is not changing with time. This is not actually stationary. Stationary, we should call a process stationary, a random process stationary. These are uh, in this scenario, we should call the Markov decision process is homogeneous. That means in every step, the transition and the reward is same. So we are initializing this, instantiating the MDP and the horizon. Now, this is the validation algorithm. So in the first step, what we did, we initialized value at step H and policy uh, as an empty set. So here we are initializing as 0 functions, all 0. So that is kind of same. So we'll update on the board. And value also for H plus 1 step, we are just initializing 0 and then we'll update. Okay, I think we can update. We missed this H step update. V H Well, another thing, we have missed this terminal reward as well. So let us so we should also return the terminal reward. Size is NS. Well, so in the step, you have to pass the step as well. In MDP also, you have to pass the horizon, because otherwise the MDP will not understand which step it is in and cannot return the terminal value function. Self.h equals to h, and here basically you have to if h equals to self.h, then return self.r and self.tr. TR stands for terminal. And none, that is next state is none. And self dot tr is. I hope this is correct. And here I have to pass the horizon as well. Yeah, hope this is fine. So all this is not, these are not needed for value iteration, because just RH is needed, because we are not taking a step here. Okay, so we are not simulating the Markov decision process. So that we can do, we can do it later, but not now. So here it is basically MDP dot TR terminal reward. Yeah, that's it. That will be a vector, and that will be stored at VH step. Fine. Then I think two initializations are done for H in range capital H. So this H variable here is different than what we have written in the pseudocode. So here H is going from 0 to capital H minus 1. So we have to while storing the value, you have to just subtract it from capital H. So the effective this index will be basically equal to small h in the pseudocode. Okay. And then for every state, we initialize a Q function. I think Q learning you have a Q function you are you introduced to. Okay, just
Yeah, in the context of multi-arm bandits.
okay, fine.
It's the
So
expected reward, right?
here it is not that. Anyway, so don't worry about that. That is just a variable here, but basically Q, we call something Q value function, and that's why it's Q here. So, okay, after answering this screen, I'll come back to pad and there I'll discuss. Okay, so Q is initialized as empty dictionary, and for every action, we store, for every action, we store the reward at state A and S, sorry, state S and action A, and then we add the expected next value, next state value, and which is this, which is exactly this, that summation P is A S prime times value of next state at next step. Okay, so, and the value is basically at that step is basically the maximum of this use, the maximum value in stored in this dictionary, right? And the policy is whichever key or whichever action is maximizing that. Right. So that way we are basically doing whatever the pseudocode told us to do, and yeah, that's it. We are returning the policy and the value. So I mean, this value is basically value at every step. So in that pseudocode, I think I only returned V0. That we are not doing here anyway. So yeah, that's it. Hope this will run fine. So I'm basically printing this policy and then okay. See what happens. Okay, so see these policies. So it says that first step you apply this policy, second step you apply this policy, third step, and so on. Okay, see that all the policies look same. Okay, but at the last step, it's different. So this 4 is different. So it's not a stationary policy, right? And I mean, this is almost stationary. Like in the last step, at one step, the action, optimal action is changing. But there are examples where uh, like there are more changes, more sort of non-stationary. And this is the value function. This is at step 0. What is the value function? Step 1, what is the value function? If you can see that value function is increasing. So sorry, decreasing as h10 goes to small h goes to capital H. And at capital H, we have initialized it as the reward function. So that is the terminal reward function, reward matrix of vector. Okay. Okay, so that's it. You can download and try out different things. You can simulate a trajectory, see how the reward, and also you can what you can do is you can fix a policy and then can evaluate the policy. What is the value at of the policy at different states, right? Okay, so this part is done. Okay, so as saying that Q value function, basically value function is a function of state. I'm not writing the H or anything. Oh no, maybe I can write VH is at S is max over actions, or sorry, new, I think, new is A plus expectation over next state, EH plus 1 is summation over this. So VH is a function from state to reals, right? And this thing we can call Q value function or action value function. This is called value function. This is called action value function or Q function. This is basically without this maximization, whatever inside. So if you remember in the code, we have basically stored this thing in that dictionary Q, right? So that was the that was the reason for the naming. Oh, that's it. Yeah. Nothing more. Okay, then
If we have to correlate this slide with the code, you are saying that it's a 40-step Markov process for 40, uh, 40, I guess the horizon is 40, means that
capital H is,
whatever process runs, it will run 40 times.
sorry, whatever.
So whatever process you are finding the optimal policy for, uh, so what is this horizon in this case?
40.
What is the horizon?
So
What does it mean actually, the horizon? So can you explain in terms of like a real world thing where the horizon is in
okay,
real world, this process runs 40 steps, or is this some kind of a iteration? You run the iteration 40 times.
no. Yeah, so it's both basically. So for the MDP, the process runs for 40 steps. I mean, when you are like in real world, MDP is basically a real world system, right? So say there is a chemical plant and there are some inputs. I cannot imagine what the inputs could be, but there are some inputs and there is some state variables as well. So say that process stays for 1 hour, and in every 5 minutes you you can change your input, and every after observing the state, okay, and every 5 minutes for 1 hour, right? So you have 24 steps. So that is basically finite horizon MDP with 24 uh, horizon or episode duration as 24. Okay. Now that is same as the iteration in value iteration, because in what dynamic programming or value iteration said, you start from I mean, you know the entire system, the transitions and the rewards all. So this iteration has nothing to do with the real life simulation. This is just you do it in your computer. So you start from the last step, follow this algorithm, you will get your optimal policy for every step. And for every step,
So that 40 has got nothing to do with the actual process 40.
yeah, it has to. It has to.
No. So you're saying that there is some process in the real world which kind of in an hour, let's say it runs 12 steps, right? In an hour. Every 5 minutes runs once, 12 steps. And what you are doing with the algorithm over there, that H, that
Yeah,
was just iteratively finding the optimal policy and nothing to do with that 12.
no, it has to do with the real, because it has nothing to do with the real life, like one run of that system. You are doing it entirely in your computer and not in the cloud. Okay. So this is just computation. And yeah, this has nothing to do with the real process, but the age will be same, because you have there you have to take action for 12 times, right, in 1 hour. Here also you will find 12 the optimal policy for all these 12 steps. And that's why these iterations are will be exactly 12 iterations.
Okay.
Okay. Yes, so that was for finite horizon MDPs. And there is something called stochastic shortest path problem, or where it's finite horizon, but your horizon is also a random value. I think that Professor Ravindran has already covered that. If you want to study more on that, you can follow this book called okay, Sarton Barto is also reference. So I studied
One
from.
question. Where did you get a terminal reward from? What is the meaning of the terminal reward?
So that okay, so one example could be like so I have given an example in tutorial 2 on which was about inventory control, right? So there terminal reward you can think like okay, that in that sense it will be cost. So at the end, whatever will be remaining, you cannot sell that. So say uh, okay, so finite horizon cost in this inventory control problem, you can think like that. There is a carnival going on, and that lasts for 7 days. And at the seventh day, if you say you have given a food stock, and at the seventh day, if you have some inventory left over, and say those are like something like milk, uh, that will be spoiled. So if you have 10 liter of milk for left at the last day, that is a very bad situation for you. So that entire milk, say it will be spoiled. In ideal situation, you may find seller, but anyway. So that is kind of terminal cost. And reward, I think the negative of that is rewarding.
Okay.
Yes, so where was I? Why did I write this optimal? Okay, the book name. Optimal control and so volume 1 can read. So chapter 1 is for finite horizon. And chapter 7, I think chapter 7. The last chapter is not 7. So stochastic shortest path. Discounted. And also there is average cost or okay, so in the setup in this book is by so setup in this book is basically minimizing reward, but that is same as maximizing reward. So minimizing cost, that is same as maximizing. Okay, so let us move to infinite horizon discounted reward MDP. So this SSP, I am not going there. That is this SSP and discounted reward MDPs are kind of same. So analysis would be similar. And for that, if you read chapter 7 of this book, you'll understand. Okay, so a new topic. In finite horizon. Market decision process. So that is described as the state space, the action space, P. Here we will not assume non-homogeneity. That is here the transition pattern and the reward function are homogeneous. That is for every time step they are same. Satisfying that assumption that it's a probability handling. Okay, let me just not write this, all those things. Here. And gamma, where gamma belongs to 0 to 1. And this is called discount. If you are not familiar with this notation, this is including 0, excluding 1. Okay, so it cannot be gamma, we are not considering to be equals to. Well, so in this analysis, whatever we are going to do, there also you'll assume that state space and action space both are finite. Okay, so what is our objective? Say there is a policy. Policy pi. If you want to apply a policy on this Markov decision process, you have that has to be an infinite policy, right? Pi 0, 5, P1. So the value of policy pi is defined as P pi S0. Or just write S as expectation over pi. Summation running from 0 to infinity, gamma raised to t, mu st not at. We are taking action as per t or policy pi. So I'm assuming here that policy is deterministic, but I think we may not consider that. But for the timing, we just go with deterministic. Given that S0 is smallest. Okay, so two assumption. A1. A1 is cardinality of action state space and action space is less than infinity, that is finite, and A2 is mu. Okay, this I think already, no, I have not written. So mu is a function from a state action space to 0, 1. So just to say that mu is bounded function. Okay, if this is true, the second one basically, then can you tell me that what is the bound on V pi? So what is V pi will be always positive. So what will be max? Is minus V pi max. What can be its bound? Anyone? Just geometric series, right?
1/1 minus lambda maybe,
Yeah.
or gamma, sorry.
Oh, no. Oh, is it lambda in the lectures?
No, it's gamma. Yeah.
Yeah, if there is some station mismatch, please go over it. And yeah, so this is something finite. So I mean, this is something well defined. Well, so uh, then what is optimal value? In finite horizon, we have seen the optimal value function. Right? So here also we can add something, and we have to define them. The optimal value function is defined as Mr. is super all policy pi. So this is basically the universal set of policies, capital pi, p pi. Uh, now you also define that what is optimal policy. Optimal policy is one that attains this V star. That means optimal policy is the if or read it like V star is an optimal policy if V star is equals to V of itself, not V star, pi star, right? V pi star for all is instances. Well, now is it proved in the lectures that a stationary policy will, sorry, yeah, a stationary policy will always be maximize this, or is it just discussed? I think it's fine.
I think it was just discussed that there was a question raised that why should each of these state be maximal? I think we took it for granted that each of the state is maximal.
Yeah,
When we say optimal,
that's how it is defined, and it can be shown that there could exist one policy there will exist one policy that will maximize all of these states. So the reason basically, if you start from T and
So I
look
think
at
if you think about the policy as that linear function, then it was proved actually that the linear function applying that linear operator again and again on the one arc space will lead you to
no, no,
that fixed point.
that has nothing to do with policy, I think. Okay, so you are saying something else, which we'll discuss today. But what I'm saying is, say you are at state S here, okay, at T equals to 0. And I'm saying why this policy will be stationary. Stationary, right, as in at, I mean, phi star will be some function, sorry, pi star will be some function, phi star, and so on. All are phi star. Okay, why? That is because at state S, if you apply policy pi star S, sorry, pi star 0. So say at state S, this is a collection of these functions, right? P0 star, or what should I call it? P0 comma 1. P0 comma 1. I'm not considering it to be uh, non-stationary, sorry, stationary policy. P0 2 and so on. Say you are applying this policy at state S at time t equals to 0. Now consider this at state, if you arrive at state S at time t equals to tau, then from here also you need to apply the same policy, right? And when you will arrive at state S, you do not know beforehand. So you are at state S at time tau, and here also you have to, like, your value. If we define your value here, that will be exactly like, I mean, the policy value of the at this state, and I mean, what should I call it? Future value. Okay. P pi S tau. That means it's starting at tau. So expectation you just imagine, and given expectation I'm not writing, given S tau equals to 0, and that is same as this, right? So here onwards, if this point onwards, I'm saying pi star 0 is optimal from this point onwards. So pi star 0, same policy is optimal from this point onwards as well, right? So that is only possible if this is stationary policy. Otherwise, it is not possible. Okay. So fine. Next, we'll discuss Bellman equation, and why this Bellman. We'll first try to understand this intuitively, then we'll prove. I mean that Bellman equation holds. Wait, let us fix a policy. Fix policy phi from any policy. It can be anything like stationary administration. And initial state, yes. V phi S is defined as expectation over policy phi sum of reverse equals to 0 to infinity gamma raised to t r or mu. What I am writing? Okay. Did I shift to r somewhere? Okay, mu here. Okay. In the last step I did. Mu here also. Mu is t at. So AT is played according to the policy, whatever it suggests. Randomized or deterministic. Everything is taken care of that. S0 is S. Now, so at time equals to 0, gamma raised to t equals to 1, right? So let us separate this. ST, oh sorry, S0 is 0, A0 plus equals to 1 to infinity mu ST at given S0 to S. Let us separate these two terms as well. If I mu. So S0 A0 mu of S0 A0 given S0 equals to S is basically mu of S comma A0, right? Because S is already fixed. Only randomness is there on A0, and that is in randomness is there only if the policy pi is randomness policy. Otherwise, it will be phi 0 S. And then phi pi okay, gamma I have missed. So let's take one gamma out. Then it will be t equals to 0 to infinity gamma raised to t times mu of st plus 1 at plus 1. Right? Given S0 equals to S. Now let us consider this okay, let's just okay, I'm not okay. This separation was unimportant actually. Let's not write separately. S A0 plus gamma times. So this thing is exactly V pi st plus 1, right? It's starting from st plus 1 and st plus 1 here is a random variable. Now, if we just relax this random variable, V pi, say phi is randomized, let us take the general case. So probability of playing A at state S is P A given S. So this will be summation over set of actions A P A given S mu S comma A plus gamma over this is given 0 equals plus summation P S comma A comma S dash. Okay, what is the probability that it will take action A? Hello. So at state case, what is the probability that it will take action? So this is basically the probability that current state is S. What is the probability that next state will be S prime? So this we are taking this summation. Okay, I should write different. So I should write like this first. Prime is what is the probability that current state is S under say policy pi. Current state is S and next state is S prime times V pi S prime. And this P pi S prime that can be again written as write the first term plus gamma S prime S. Then summation over all actions the probability of playing action A given current state S, and then given at current state S, we have played action A. What is the probability that we have landed up in state S prime in the next state? So this inner summation is basically this object times P prime S prime. Well, so this was just unnecessary math I did. If you just consider this as deterministic policy, then all these are not required. And so let me write that as well. But this exercise is nice. Just it may clear some doubt. So deterministic policy, what will happen is we'll have S P S plus gamma times P So PS is S prime times V by S prime. And what is equals to? This is equals to V by S. Well, so this is a nice recursive equation, right? So here we have considered this policy to be stationary, and okay, let us not do that. So we're just going to replace pi with phi. That is not required. Anyway, so this is a nice recursive relation. Now say there is a optimal policy. What is an optimal policy? P star, sorry, pi star is optimal if V pi star is equals to sup over pi capital pi V pi S or all S. So pi star is basically a policy rate, and hence V pi star is will also be equals to mu S PS plus gamma S prime S P S PS S prime, the next data value. Yes. So let me call it phi star, the individual functions. So this is just the intuition for Bellman equation. This is exactly what Bellman equation is, right? And then we write that this max whatever. So, but this is what is the intuition. Now we'll, I don't know how much time we have. Half an hour. So yeah, if I start, I'm afraid I cannot finish that. So for today, let me just write the pseudocode and then code it for yeah, for the demo, and then we'll conclude. And in the next tutorial, we may try to uh, see the convergence guarantee of value iteration and proof of this Bellman equation. So value iteration, pseudocode. So input is again the DP, which includes the state action space. Uh, so the transition probability kernel, the reward function, and the discount factor, the DPM, which is all these elements, the 5 tuple. Yeah. And for like, uh, it will converge definitely, but we need to stop the algorithm in finite time, right? So we may also uh, introduce an error tolerance, which is small enough. Tolerance. Excellent. So initialize V0 to be V0 to be 0. So it means basically for every s, V0 s is equal to 0. And some a, which is basically the iterate, that is equals to 0. Then for, okay, so if the error tolerance, which is some difference between previous value and next value, if that error, I mean, if that difference between next value and previous value that goes below epsilon, then we'll stop. Otherwise, we'll continue. So we'll do it by while loop, while two, two, and then we'll check this condition. And if that condition satisfies, then we'll break the while loop and come out. We update k as k plus 1. And for is in state 2, we'll again like you can store these q values, but let me write that in just one line. This vkx is, or just write it as we should write. Initialize q to be there is not an initialization. So SA QSA equals to RSA plus, sorry, mu, right? Mu SA times gamma times this expected next state value. But this is not value exactly. Okay. So yeah, one difference is in finite horizon. Whatever we are computing in the iterates are exactly the value at that function, that point of time. So we are computing VH. That means this is the exact value. But here it's not like that. Value doesn't have a notion of time. So value, there exists only one value function, which is like true for all time. And this is basically an like this should VK. We can show in that theoretical analysis which we're supposed to do today. That shows that this VK converges to V star. Okay. Okay. As this iteration go on. Okay, so what we do is then again something wrong is we have to compute for every S, right? Sorry, every A. So there should be another for loop for A in A. And then we end this for loop. Then we need to update two things. One is the value and then the policy. Why we need to update the policy? That is, there could be two ways of stopping the algorithm. One is you check two consecutive policy that are returned by this algorithm. If they are not changing, then you stop the algorithm. Or the difference in value, what I told earlier, if the difference in value doesn't change much, it goes below epsilon, then you stop the algorithm. So either way, it's fine. So Vk S is basically max okay QSA and Vk S equals to argmax, the action. Well, then if so, we have to end this for right. Sorry, we are not we are inside one for loop. Yeah, we have to end this for. And for and here there are two possible conditions to break this while loop. One, if max over states Vkx minus Vk plus 1 s that goes below epsilon for I'm expecting we'll take sufficiently small epsilon, then red and if minus y well, and there is another possibility that is if Pks equals to Vk s sorry Vk minus s Vk minus 1 s for all s then well so that was the algorithm and then at the end return Vk what is the value and Vk. Okay, so do you want me to code this? If not, then we'll end this here. And if yes, I'll do it. Okay, before that, I think today we have some time. Um, may I ask you if anyone here wants to work in reinforcement learning in future or in what stage of your career you are now?
So I desire to use reinforcement learning as a principle. So basically, I'm an algorithm designer, and I want to use reinforcement learning as a central principle on just making the algorithms better in the hands of the user. Uh, so that so
So,
more than one occasions we don't have data available once we ship the
right,
algorithm, right? So so let's say if it's a control algorithm or a vision algorithm, if we have an element of reinforcement learning in there, there is a possibility that if we design the feedback system, that we can make the algorithm better in the hands of the user. So that's my motivation to do reinforcement learning.
right. So yeah, that is online learning is one of the way to do that, right? Nice. And others? So I'm guessing you are working profession.
Yeah, yeah. Actually, I'm self-employed currently.
Oh, okay, others? maybe others are sleepy for my boring lecture. So, okay, we'll move to coding. Yes. Is the screen visible? The coding.
No.
Now,
Yeah, visible. Yeah.
okay, same class of MDP. Just modifying it. There will be no transit, no terminal uh, reward function, and there will be no
If you want to
horizon.
share this notebook, can you just like copy paste and do both so that if you're going to share this notebook, it will be convenient to have both available. If that is
Sorry,
okay.
sir. Sorry,
If,
sorry.
if you if you are going to share the notebook, instead of
Mhm.
modifying it on the current thing, you can
Yeah,
just
no,
copy paste and
no, I'm copying question. So this is a new cell I have created. Yeah.
okay,
So
okay,
you will get both. Yeah.
okay.
So, so whatever we have added for incorporating this uh, new, the terminal reward that we are basically deleting. That's it. I think there will be no other changes. Oh, so we have to, there will be no age here. Initializing the MDP of 10 state and 8 actions. Yeah, now the main part. So let me write this as dynamic programming. Program. And this one is valuation. Should have copied earlier. So with MDPH, there will be gamma passing. Let us keep 0. Okay, let us start from low value. We'll see if with changing gamma for this particular MDP, if the optimal policy also changes. The value function will definitely change, but optimal policy also could change. So there will be no age plus 1. So the value function will be just one value function. And we'll initialize it 0. Policy also we are initializing in zeros. While true for every s, we are having this q and this q and s comma a. Okay, so this is it's a dictionary, and we can just save this only for a. Fine. So instead of V H minus 1, this will be just V of next state. And here also the same thing. The S will be max of V values. And the policy, that is, will be the maximizer key of this key. And then again, else will come. And when this for loop will end, then okay, before the for loop starting, we can save this value in some other array equals to V for me. And then we have to write that if condition, if max of V minus, so we have to take also absolute value, V minus V old. Okay, take epsilon here. We have to pass gamma here. That is the most important thing. We have not written gamma yet. So gamma will be multiplied here, right? If maximum of this difference is less than x or epsilon, then break and return policy and fine. This should work, and MDP and gamma and then x is variable. Let us just write 10 to the power minus 3 or minus 4. Hope this will be fine. Yeah. Range. Let me just pass 0.8 here or 0.7 here. There is some problem. MDB has no attribute called NS, okay. Doesn't look like that. It has. Oh, it has to pass. Oh, sorry, not MDB. We have initialized it at AM, right? This is something wrong. No, it's okay. Here we are writing. V only is not defined. Okay, let's everything. So okay, so see the value and also this policy, right? The values are very small. If we increase the gamma, then what is expected? The value will complete my sentence. If we increase gamma, value will.
So if you increase gamma, you are looking further into the future. Probably increase.
Yeah, so we are giving more weightage to future. And also we are not decreasing the weightage to the nearby values. So ultimately it will increase. That's what happened, right? But the policy didn't change. Okay, let us increase the gamma a little bit more, 0.9. Policy is still the same, okay, but the value has increased 0.9. 0.95 maybe. The policy is still the same. I don't know, maybe it will be same.
Maybe we should
to,
decrease. We should make it a little more short term. Then the policy will change.
Sorry. What did you say?
Maybe we should make it more short term.
Yeah, right, right. If it is yeah, then policy may change. Okay, let's try something extreme. And then you'll go to the lower values. So this is taking more time because it's taking more like gamma value is very high. So it will take more. The value will be first of all very large in the order of 10,000 or 1 lakh. And the time for convergence will also be very high. So if you want to study this, the theoretical analysis of this, please go through the Versicus volume 1. Here you'll understand this. What is the rule of gamma in convergence? What is the rule of change of policies? Okay, so it seems it is kind of stuck in that loops. Maybe we can stop it here. We'll take 0.1. It will be very small. Yeah, now the policy has changed, at least at one place. Okay, so that was it. So what you can try is take a policy and evaluate, write a function for policy evaluation, and which will give you basically, if you input the policy pi, it will return in the value of like v pi, what you have wrote in notes. Okay, you can try those things. Yeah, so that's it for today's tutorial. And yeah, I think you have, all of you have my mail ID. Is right if you want me to cover some topics. If you have some questions, you can ask me.
Thank you.
Oh, okay, so if you have no questions, anyone, you feel that you can end the meeting here.